implementation of the Octree algorithm. Before explaining to you all the details you see here, let's take a look at an example in 2D instead. So let me explain how the algorithm work in 2D using this beautiful drawing. So let's imagine that we have this scene around here and we have our marble just touching the square right there. So looks like we will have a lot of collision checks to do because we have to check with every shapes in the scene to know with what the shapes we are colliding with. But using the Octree algorithm, we can remove most of those checks and just not do them entirely. And how it does it is that instead of checking all collision possibilities, we are dividing the space in 4 quadrants. So let's draw our quadrants right there. So now we can eliminate a lot of collision check. All the shapes in here, we don't have to check them at all because we know our marble is not in this quadrant. So we have like a dozen collision check we can simply not do. We only have to check the shapes that are in this quadrant. But this algorithm is actually recursive, so it will do that again to remove even more checks. So instead of checking with all of the shapes in this quadrant, it will divide space in 4 again. And now we have even less checks to do. We only have 2 of them. Technically, we could stop here because there's not a lot of checks, but we can also divide even further and do that. Oh, it's a bit, yeah, and do that. And now we can see that we are only left with 1 collision check to do. And if we're doing this 1 check, we'll see that we have collision, but we did only 1, 2, 3 overlap tests with the space divisions, and we eliminated dozens of potential collision checks to do. And now let's go back to 3D. What you see here is the exact same thing I showed you in 2D, but now instead of square quadrants, we have cubes. And also, since we're adding 1 dimension, we need 8 cubes instead of 4 squares. The red cubes with the white borders you see here represent where the algorithm is descending into to narrow down the amount of collision checks to do. And the tiles that appears in green are the output of the algorithm and the tiles that are potentially overlapping with the marble. Now let's take a look at what the algorithm is doing while we're moving the marble around. It may happen, like right now, that the marble is in between the border of 2 cubes. To include all potential collision, the algorithm must go into 2 different cubes at the same time. Also, in this case, there's a limit on how much the Octree will divide itself. Here we set a threshold of 8 elements inside a single cube before dividing it further. This is to avoid having the cost of the algorithm being higher than the cost of simply checking the collision 1 by 1. We can really see this in effect when I'm going to a region with much lower tile density. That's it for explanation. Let's roll the music and enjoy the visualization.
One example of a tree data structure that's used very commonly in video games is something called a quad tree. Now, quad trees are in 2 dimensions, and there's also these things called octrees, which are used in 3 dimensions. But I'm drawing this on a 2D sheet of paper, so we'll talk about quad trees in this example. Now, quad trees are a way of representing objects inside of your game spatially near one another. So it can help speed up doing really quick queries on what is nearby me, or give me the list of all of the targets or all of my enemies in one given area. And I'll show you exactly how that looks. So if you imagine this whole sheet of paper as our game world, and we have a whole bunch of people running around inside of it at various locations, right? You could think of this as a really large MMO or some sort of RPG game, and maybe there's some big clusters of people over here and some really sparse areas. You could think of maybe these are where the cities are inside of this big game, and we have this big MMO or open world RPG game or something else along those lines. Now, one common thing that could happen is if I'm standing at this position and I use some sort of area of effect spell that's supposed to target everything around me. Well, the question is, well, who's around me? Which of these enemies, these potential targets, do I need to possibly hit? Now, one way that you might go about doing this is saying, well, I'm going to iterate through my list of all enemies in my entire game world and see which ones are close enough to this given position. Now, this ends up being like a linear time function where you're essentially iterating through each one of these enemies, each one of these potential targets throughout your entire game world. And this can be okay for a lot of smaller games, a lot of games where it's just you and 5 or 6 enemies on the screen, and that's it. But once you're talking about something really big, like an MMO or an open world RPG, these X's may be hundreds and hundreds of different enemies. So it can very quickly get very time consuming to do all these distance checks to determine which ones are nearby. And the interesting thing is, your grenade may only have some sort of area effect that's sort of this big, and you're still doing distance checks against these enemies out here, which are obviously too far away. So one way that we can sort of split up this world is into something called quad trees. And quad trees spatially divide this entire area up into a tree-like data structure. So if you imagine we take our entire game world and we just encompass this entire thing inside of a box, right? This essentially is our root node, right? It contains everything in the entire game. And then we split this thing into 4 different sections. And we'll just do it like this. And for any of these potential targets that may be on the line, they're going to be on one side or the other, right? There's no one who's perfectly on a line like this, right? Now, what we have so far is we have this giant box, I'm going to call it A, and then we have these 4 boxes inside of it, B, C, D, and E. This structure so far, where B, C, D, and E are all inside of A, could be represented by a tree data structure like this. Here's our node A, and then underneath this, we have 4 child nodes, B, C, D, and E. Just like this. Now, each of these, this is how we get that quad tree, right? Because each of them have 4 children. Now, each of these spaces could be further subdivided into 4 other smaller components, right? I'm just going to do it on this area here because it's the only one that we really care about for this example. Right? So B, C, D, E, and then this might be F, G, H, and I. So inside of E is F, G, H, and I. Inside of E, so inside this node here is F, G, H, and I, right? These are 4 nodes that are underneath my node E. So the interesting thing about this is if I have an enemy at this position here who's in this box F, well, they're in this node here, F. And F is also inside of E. And E is also inside of A. So if I were to query to my game space saying, give me all the enemies that are inside of A, I'd be querying, give me all the enemies that are inside this entire space. If I said, give me all the enemies that are inside of F, I'm only querying this tiny little box down here, right? So I'm subdividing this space out into these smaller and smaller quadtrees. Now, in this example here, if I have a grenade and it has this area that's about this size, right? We can say, okay, it overlaps D a tiny bit, right? We could say that this space here is larger than H, right? And E contains F, G, H, and I. Right? So by looking at this box E, we're looking at this entire space. And then, because I have this slight overlap here, we may also look at E as well as D. Well,
In our example, since it's a two-dimensional plane, we have exactly two properties, the x-coordinate and the y-coordinate. So the root node starts off arbitrarily picking one of those. Let's suppose it's the x-coordinate. Then its children, the second level, alternate to using the y-coordinate. The grandchildren nodes cycle back to using the x-coordinate, and so on. When inserting a new node, just like in a typical binary search tree, we compare the node's value and go left if it's smaller, right if it's bigger. It's just that, as we go deeper and deeper down the tree, we keep alternating between using the x and the y values in the comparison. Note that in our example, since we started with comparing the x values, the y values were ignored, and as a consequence, the second layer nodes break the binary search tree rule, where all the nodes less than the root are on the left side, and vice versa. But amazingly, it turns out that this is okay. The magic here is that we can check for this inconsistency on the way back when unwinding the recursion. Visually, you can think of the root node dividing the xy plane into left and right sides, since we decided to start off with using the x-coordinate. Then the next point will fall into either the left or the right side, and in turn, divide that side into top and bottom sections. So as more and more nodes are inserted into the tree, each point splits parent section into two subsections, alternating between splitting the section into left and right versus top and bottom. Suppose our target point is 9, 4, and our goal is to find its nearest neighbor. So we walk down the tree and keep calculating the shortest distance found so far. Note that on the way down, we missed the point 10, 2. This happened because when comparing with the second node of the tree, point 13, 3, the y-coordinate was smaller than the y-coordinate of our target point, 9, 4, so we traverse the tree by going right. Once we have gone as far down as we can, we then recurse back as you would in a regular binary tree search. We do have a candidate closest neighbor, but there is a possibility of a closer point still. Think of the shortest distance as a line going from the target point to the candidate point. Let's call this line R. This line is probably going to be at some random diagonal angle. But
I thought we'd continue looking at points and point clouds. Last time, if you recall, we talked about the iterative post point.
KD tree is a data structure useful when organizing data.
Suman. Today I am going to show or discuss what is the K tree.
KD tree is a data structure useful when organizing data by several criteria all at once. Consider an example where you have a set of points on a two-dimensional plane. Now, suppose you are asked to find the nearest neighbor of some target point. What data structure would you use to store these points to be able to solve that problem? A naive approach would be to perhaps store the points in an array sorted by one of the properties, such as the x-coordinate. Then you could easily do binary search to find a point with the closest x-coordinate, but unfortunately, you'd still not necessarily be any closer to finding the point where the y-coordinate is also nearby. To convince yourself of it, just think of the case where all the points share the same x-coordinate. Clearly, you'd have to examine every single point one by one to find the nearest neighbor of the target point. Hello and welcome to StableSort. KD tree data structure is very much like a regular binary search tree, except instead of holding just one value in every node, it holds k values. When traversing a KD tree, we cycle through the index to the values list based on the depth of a particular node. The k in the name KD tree refers to the number of properties that each data point has. In our example, since it's a two-dimensional plane, we have exactly two properties, the x-coordinate and the y-coordinate. So the root node starts off arbitrarily picking one of those. Let's suppose it's the x-coordinate. Then its children, the second level, alternate to using the y-coordinate. The grandchildren nodes cycle back to using the x-coordinate, and so on. When inserting a new node, just like in a typical binary search tree, we compare the node's value and go left if it's smaller, right if it's bigger. It's just that, as we go deeper and deeper down the tree, we keep alternating between using compare the node's value deeper down the tree. Go left if it's smaller, right if it's bigger. It's just that as we go deeper and deeper down the tree, Note that in our example, since we started with comparing the x values, the y values were ignored, and as a consequence, the second layer nodes break the binary search tree rule where all the nodes less than the root are on the left side and vice versa. But amazingly, it turns out that this is okay. The magic here is that we can check for this inconsistency on the way back when unwinding the recursion. Visually, you can think of the root node dividing the xy plane into left and right sides, since we decided to start off with using the x-coordinate. Then the next point will fall into either the left or the right side, and in turn, divide that side into top and bottom sections. So as more and more nodes are inserted into the tree, each point splits parent section into two subsections, alternating between splitting the section into left and right versus top and bottom. Suppose our target point is 9, 4, and our goal is to find its nearest neighbor. So we walk down the tree and keep calculating the shortest distance found so far. Note that on the way down, we missed the point 10, 2. This happened because when comparing with the second node of the tree, point 13, 3, the y-coordinate was smaller than the y-coordinate of our target point, 9, 4, so we traversed the tree by going right. Once we have gone as far down as we can, we then recurse back as you would in a regular binary tree search. We do have a candidate closest neighbor, but there is a possibility of a closer point still. Think of the shortest distance as a line going from the target point to the candidate point. Let's call this line R. This line is probably going to be at some random diagonal angle. But if the line directly perpendicular to the section that we chose not to visit when recursing down is shorter, then there's a chance that that section may have a closer point. So this is where the magic happens. As we recurse back, we also calculate the distance to the section that we did not visit. If that distance, let's call it R prime, is smaller than the best distance found so far, then we traverse into that section as well. But note that this does not mean that we visit every node in the tree. If the height of the tree is h, then at most we'll visit 2h nodes. In other words, this is still a logarithmic search in respect to the number of nodes in the tree. Here's a pseudocode for the nearest neighbor function. We mod the depth of the node by the number of dimensions that the tree uses. So as we go down the tree, the depth is incremented, but mod operation cycles through the values that are being compared. Choosing which branch to follow is very much like a regular binary tree search. But on the way out of the recursion, we check if the radius is greater than the distance to the other section of the plane. That's the magic line. Just a couple of final notes. The closest subroutine simply chooses between two passed-in nodes without recursing any further. And we don't bother taking the square root of the distances and just compare the distances squared so as to save some CPU cycles. For the full source code, see the link in the description. So far in our example, we've been using a two-dimensional plane. But the methodology works equally well in higher dimensions. Each node would still have a left and a right branch, but the number of values in each node could be arbitrarily large. Suppose you are designing a database for a hospital that keeps track of each patient's blood type, white blood cell count, and blood pressure. Then a new patient comes in with an KD tree is a data structure useful when organizing data by several criteria all at
I thought we'd continue looking at points and point clouds. Last time, if you recall, we talked about the iterative closest point algorithm, and the idea was we have a load of points, we have a load more points, and what we want to do is try and move them closer together and align those two meshes. I mean, they're not meshes, they're point clouds. With a view to maybe doing a 3D reconstruction or something like this. Now, this is actually really, really common, right? In 3D, sure, in 3D modeling, you might do this. You might do it to reconstruct bunny rabbits. But you might also do this on a street scene. Suppose you're a robot who is going through a scene and you're doing these periodic LiDAR scans. You've got to take what you just scanned and put it up against the 3D that you've already scanned in the previous frame. And you've got to do this really, really quick. Because if you don't, you're going to get waylaid by the 60 hertz rate of your LiDAR scanner. What we're going to talk about today is something called a KD tree. Or a k-dimensional tree, and it's a neat little data structure that allows you to very quickly find what the closest point is, given, you know, possibly millions of other points. We're going to look at this mostly for my poor brain in 2 dimensions, right? But this could be 3, 4, 5 dimensional, and it could be n-dimensional, or should we say there are k dimensions. And it's like k-means. Didn't we do k-means? It's the same kind of idea, right? We don't know how many there's going to be until we actually have to implement it. But actually, the algorithm is exactly the same if you do it in multiple dimensions. It gets that a little bit slower. So I've got some points here, and what we're going to pretend we're doing is trying to find closest points to some arbitrary points. So suppose we pop down our finger here. What's the closest point? Well, it's this one, and that's easy for me because I can see the whole picture. But there's a question basically, if you're writing a computer program to do this, what's the best way of implementing this algorithm? Right, so I've got a point, let's say it's, 5, 5, something like this. All these points have coordinates in x and y. Right, so I mean, just to be clear, this is x, and this is y, and maybe we have a list of these points in memory. So we could say, okay, so if the list starts with this one, so that's the distance we're looking at, and then we look at this one, and that's the distance is slightly closer, so that's now the next closest. This one's further away, this one's further away, but this one's closer. And we can go through each of our points in turn, and eventually, if we record the current minimum distance, we'll find the nearest point. But you can imagine that for points more than this is going to be a problem really, really quickly, right? For thousands, for millions of points, possibly billions of points in a 3D scan, this is not going to work. What we do is we arrange these points in something called a data structure that allows us to better index and better search them, right? And there are a few data structures that off the top of my head that you could do this with. Octrees, for example, or something that we could maybe look at another time. But I like the KD tree because I think it's neat, and I've actually used it a couple of times in research to find closest points to things. So these are our points, and we're going to imagine that for now, they're not moving about, right? They're not moving about. These are our reference points. We want to find the closest point to here, or the closest point to here, or something like this. And we need to do that as quickly as we can. So what we're going to do is we're going to construct a data structure that represents these points in a different way to a list, so that when we actually want to search through them, it's much, much, much quicker. So what we're going to do is we're going to split up our points into 2 groups. And then for each of those groups, we're going to split them into 2 more groups. And we're going to complete this process until, you can't split them up anymore. And then, every time we have a point, we can very quickly whittle down where we're going to go. So, suppose we wanted to split up this point set. If you're looking at this point set here, where would you split it, intuitively?
Well, somewhere in the middle, across the middle.
Right. Splitting it here doesn't make any sense. Right? That's a waste of time because if you happen to be looking for this point, it's an absolute winner, right? But if you're looking for any of the other points, it's hugely slow. So yes, binary trees tend to split things in 2. So that's what we're going to do. Right, so I'm going to use let's start with my blue pen. And so we're going to pick a dimension. Let's split across the x dimension, right? And we're going to choose the median point, so the point in the middle. Now, I've left a little gap to make my life easier, and it's this one. So what we're going to do is we're going to do a split up like this. And we're going to split the data in 2. Now, actually what we're doing is we're constructing a tree, so you don't actually physically draw these lines in. So you imagine these are stored in memory. Maybe this is point A, perhaps. So what we're going to do is create a tree where the root node is point A. Right? And I'm just going to sort of do this and hope it works. Okay. Now, suppose you wanted to find what was closest to this point. It's probably a safe bet that the place to look is this side of A rather than this side of A. That's kind of where we're going. But let's take this process a bit further. Let's split here. Now, we've got 2 dimensions to split, and so a nice convention would be to alternate splitting. So we split first in X, and then we sort of divide it into 4 by splitting in Y, and then we do X again, and so on. So let's do it, I don't know, with this orange pen, right? Sort of got a strange mismatch of pens here. So we're going to split it roughly in 2, so 1, 2, 3, 4, 5, 6, 7, there's 7 points. So this point is roughly in the middle, right? And so we're going to split it here, like that. And we're going to do the same for this side. So 1, 2, 3, and so we're going to split it about here. And they're not split in exactly the same place. So the interesting thing about something like a quad tree is that they divide everything into 2 every time, spatially. So you would always split it into quarters and then eighths and sixteenths and so on. But in here, we actually split it on a point that exists. So let's continue this. So this is B, and this is C. Right, and so we're going to have B as a child, and we're going to have C as a child here like this. We're actually constructing a tree. Now, of course, these have points associated with them. Right. So let's keep going. Where would we split this? Well, probably in the middle. So let's split this one here, like this. This one here, we're going to split here. Is that right? Yes, I think that's right. And then this one, and this one. My lines are not really straight. That's not really how 2 dimensions works, but we won't dwell on it. And then finally, we're going to split here. So actually, I mean, as an example, I'm not going to draw out